We're going to learn about gases this week, next week, and probably the week after. Two very cool labs on gases. One of them will look at the relationship between volume and temperature of a gas, where you will heat it up and then rapidly cool it. The other one will involve lighters, where you will try and determine the universal gas constant R, and we'll get into the lab next week. Today we're going to talk a little bit about some basic properties of gases. Most of these properties will be reviewed from middle school. We're going to get into the gas law relationships. That is very math-based. You need to have good knowledge of variable manipulation, and we will work on that. And then we're going to link gas laws back to stoichiometry, and most of you just saw your test scores. They are very, very high, so clearly you have an extremely good understanding of stoichiometry, and the linkage there should be very simple for you. In regard to gases, we want to compare properties of solids, liquids, and gases, and there's a whole table here for you. We're going to keep it a little simpler than that. Let's say we have water in the solid state. How would you describe the arrangement of the particles there? Definitely arranged pretty well. It's like you sitting there right now, tapping your feet, vibrating in that seat, but you're not changing positions. So, definitive rigid structure, very organized particle arrangement, very little movement. In contrast, now if we break some of the intermolecular forces, what intermolecular forces exist between water molecules? Hydrogen bonds, the strongest of the three. What are the other two? LDF and dipole to dipole. So you're remembering those IMFs. So now we're going to break some of those IMFs, and we've got water in the liquid state. And now those particles are moving much faster, far less particle arrangement, much more movement. Some IMFs broken. They're not moving that quickly, so some can be reformed. But in the gaseous state, the particles are bebopping around, moving in a straight line fashion, only changing position when they collide either with each other or with the walls of the container that confines them. And so gas molecules also will exert pressure on the walls of the container. Very little particle arrangement, a lot of movement with gases, all IMFs severed in that state. So if you look at that, you can see a lot of what we saw right here. So you've just got it in an organized fashion here, but seeing it is understanding it better. Again, a solid has a rigid definitive shape. Liquid takes on the shape of the container. A gas not only takes on the shape of the container, but occupies the entire space of it. The other important point is in regard to the property of volume. What you're going to see with gases is that the volume of the gas will change when the temperature or pressure changes. You will see in your lab that when we decrease temperature by rapidly cooling that gas, the volume's going to decrease. You will see that if you alter the pressure, it affects the volume as well. And we'll talk about the inverse relationship between pressure and volume. You can see that with bubble wrap, for example. If you push down on bubble wrap, the volume of the bubble decreases. The pressure gets so great that the bubble pops. You see it with soda as well in regard to pressurized soda bottles, as well as the effect of temperature. So we're going to take a look at how volume is affected by changes in temperature and pressure in a little bit. There are many, many, many examples of gases: nitrogen, oxygen, helium, carbon dioxide, chlorine gas. I do want to remind you that 5 of the 7 diatomic gases, because this does come into play a little bit later on in the chapter, so I think if I show it to you early on, it'll really sink in. Of your Brinkelhoff series, which two substances are not gases?
What?
Just kidding.
Bromine?
Just
Bromine's a liquid.
No,
That's what I
not
said.
kidding.
I said that.
Yes.
I think you were eating. I couldn't understand what you said.
No, I said that.
What's the other non-gas?
Iodine.
Iodine. That's a solid. So these 5 diatomic elements are gases. Remember that all of group 18 are gases as well. Those are our noble gases. Fluorine's a gas.
I thought chlorine and fluorine were liquids.
No.
Okay. I missed it.
How do you put chlorine in a pool?
So right, so let's think about, so like why is fluoride in your toothpaste? So your toothpaste contains sodium fluoride. So you've got fluoride ion in your toothpaste. So how do you put chlorine in a pool?
Sodium chloride. Just kidding.
Look it up. Tell us how chlorine goes in a pool. You've got 5 seconds. Go!
Put in like tablets and then put in those things and they float across the pool. And then you say don't eat them because they're not tablets.
So do you put tablets in the pool
Yeah.
for chlorine?
We got a how-to video.
So there's a tablet. What's in that tablet?
Chlorine.
Well, look. What's that tablet made of? Let us know. Let us
Chlorine
know.
pool water chemistry fact sheet. Sorry, it was in all caps, so I had to read it.
All right, so let me know what it says, Mr. All Caps.
Ooh.
The most common chemical used in not only eliminates bacteria, as disinfecting, also
Through a use of an approved automatic chlorinator.
What do you got?
How to put chlorine in a pool. There.
Put it in the pool.
They say the liquid is poured into a pool.
What's in the liquid?
It's tricolored transvestite.
Sodium hypochlorite.
Is that what it is? Do you know what sodium hypochlorite is?
HCl. No,
H2SO4.
Do you know what H2SO4 is?
Hydrochloric acid.
No,
Trichlor.
sulfuric acid.
Sulfuric acid.
Oh my god, Hannah, everyone knows that.
That's a minor.
Sorry.
So are you putting a tablet in the pool
What's that thing?
such that you're increasing the concentration of an ion that can be converted to chlorine? See what it is.
It's trichlor.
All right, we're going to take a look at that at the end, and you're going to come up with something brilliant to share with us.
Stevenson.
Step 1, go to the pool.
Steve, you got it. Does chlorine taste good?
Calcium hypochlorite.
Calcium what?
Hypochlorite.
Well, what does that do?
It's
It
both.
is the main
Calcium
ingredient
both.
in swimming pool chlorine tablets. It kills bacteria, yeast, fungus, spores, and even viruses.
Good thing.
Just put it on the computer.
What about the urine?
Oh, it doesn't say that.
Not sure about that.
That's mostly water says.
All right, we'll come back to this concept. We'll get it, and we'll figure out how we convert that to chlorine in a form that can be used in a pool. But chlorine is a gas. Just be careful. Make sure you understand. Oh, look what I did here. Fluoride ion, right?
What's cyanuric acid?
Right? Yeah, fluoride ion. Kalish is a dingbat. All right. Here we go. I think what I was doing was thinking this way.
It says cyanuric acid. I don't know what that is. Oh, I'll read.
I'm so hungry.
Alrighty. To understand gas properties, you need to understand it through the kinetic molecular theory, and we're going to talk a little bit about the kinetic molecular theory proposed in 1860 by Boltzmann and Maxwell. I have a great little video here that outlines all of these key points. I'm going to try and play it softly off the audio system. It's a very cranky little audio system. Let's hope for the best.
If you write anything on your computer, you need to background.
I write pretty much all day.
No.
review, brushing up on what we probably already know about phases of matter. I have here indicated some certain representations of phases of matter. I have a container and some particles in it. I've got a representation of a solid, a liquid, and a gas. Let's start with the solid. The solid here, like all the other phases of matter, is made up of particles. That's these little red circles right now. Particles can be either atoms or they can be molecules that are formed by the atoms coming together. Either way, all matter and all things are made up of particles. So in a solid, the particles, as you can see, are packed together really tightly. They have very little kinetic energy. They're moving around a little bit, but for the most part, they're locked in place and they're locked to their neighbors. The particles in liquid have more kinetic energy. They're moving around and they're clear numbers. They're still locked in with their neighbors to some degree, but they're swimming around. They're swimming in close proximity to the particles nearby. Gases, on the other hand, have a ton of kinetic energy. In fact, to make this picture even more accurate, what I'm going to do is I'm going to add a few arrows. These arrows are going to represent the fact that these gas particles are in constant motion. They're moving around all over the place. They're banging against each other and they're banging against the sides of the container here. In fact, these gas particles are moving so quickly that at room temperature, they have about an average speed of 1,000 miles an hour. That's just how fast they're zipping around here in this container. So solid, liquid, and gas have increasing amounts of kinetic energy. Gases have the most kinetic energy. They're flying around in there, and they're not connected at all to their neighbors. Now, this is a very superficial representation of what a gas looks like. But often, we're going to want to look at problems and think about gas conceptually in a way that will make it necessary to have some deeper understanding about what gas is and how these gas particles behave. We obviously can't see gas, so in the problems that we're going to do later on, we have to have a way to think about it, a way to conceptualize it. So it's useful to set up a series of rules for how we expect gases to behave. We'll make these rules or assumptions, and then we can keep them in mind when we have to solve problems and do calculations. Now, this list of rules is what's called kinetic molecular theory of gases. Oftentimes it's just referred to as kinetic theory of gases. And as I said, it's a list of rules, expectations, assumptions of how we expect gases to behave. Now, if a gas follows every single one of these rules, we call it an ideal gas. But in the real world, it's very hard to come up with an example of anything that always follows all the rules. You might want to think there exists something like a perfect student, an ideal student, or an ideal kid, but rarely that's the case. Almost always we find a few exceptions to the rules. And so because of that, it's helpful to think about ideal gas, but in the real world, none of these gases that we're going to talk about ever follow all the rules all the time. At the end of this unit, we'll look at some particularly bad offenders, gases which break rules more often than others do. And we'll look at certain situations that cause gases to break the rules. For the most part, though, in all the gases that we're going to look at now, we're going to assume they're ideal gases. We're going to assume that they follow all the rules all the time. And for the most part, most of these gases only break the rules a little bit once in a while. So we can safely assume that all the gases we're dealing with follow these rules of the kinetic molecular theory. So let's take a look at what some of the rules of this are. And once again, sometimes it's just referred to as a kinetic theory. I'm going to write down here, kinetic molecular theory of gases. So in no particular order, let's take a look at some of the assumptions that we make about gases. Well, here's the first one. Gases consist of very small particles that are far apart relative to their size. This is something that's very difficult to depict visually, and I certainly didn't do a good job of it in the phase diagrams that I just showed you. Gas particles in the picture that I drew you look like they're the size of marbles in a glass jar. This isn't true at all. Gas particles are so tiny, instead of thinking of them as marbles in a glass jar, if the gas particles are the size of marbles, our container would be like the size of a football stadium. So these guys are absolutely tiny, and there's a ton of empty space between them. That's the first thing that we want to keep in mind when we're dealing with gases. here's a second thing, and this is very important. Gas particles are in constant random motion. We hinted about this earlier with those arrows that I drew, the gases moving around. The moving particles constantly collide with each other and with the walls of the container. So all the time, whenever I have gas in any sort of container, or even if it's just no room, these guys are zipping around, they're bouncing against the walls, and they're bouncing against each other. Now, let's think about those bounces a little bit more. There are a variety of ways for things to bounce into each other. And here we say that collisions between gas particles and container walls are elastic collisions. What's an elastic collision? Let's think about two balls of slime. These two balls of slime on either side of me come together, and what's going to happen? They're just going to hit each other and they go, bleh. This is what we call an inelastic collision. That means that the kinetic energy that both of these guys had got wasted in the collision. These guys were both moving, they came together and they just kind of went blah. And all the kinetic energy, the speed, the motion that they had disappears in the collision. This is like what happens if you chuck an egg against the side of a wall. It hits the wall and then it just drips down, but the motion that it had, the kinetic energy disappears. That's an inelastic collision. The collision between gas particles and container walls, on the other hand, are elastic collisions. A good way to think about an elastic collision is think about what happens when two red or pink round rubber balls hit each other. They hit and they bounce right off. Or one of those pink rubber balls hits the side of the wall, bam, it bounces right back. The kinetic energy isn't wasted in the collision. This ball hits here and it has the same amount of kinetic energy afterwards that it had when it started. That's the exact kind of collision that gas particles get into. They bang into each other and they just fly right apart, or they hit the side of a container wall and they just bounce right off. So whenever you think about gas particles colliding, you always want to keep in mind the idea of elastic collisions. Additionally, we can say that there are no forces of attraction or repulsion between gas particles. Some particles, like water molecules, kind of like each other, and so almost like weak little magnets, they tend to attract. Other particles, two particles that have the same charge, don't like each other. They're sort of afraid of each other, so they're going to repel. They don't want to get anywhere near each other. What this law is saying, when we say there are no forces of attraction or repulsion between gas particles, what we mean is that the gases are flying around and they're not going to start clumping together because they're attracted to each other. That doesn't happen. There's not that attraction. Likewise, let's assume that two gas particles are passing each other. They're just going to fly right by. If they repelled each other, zoom, they hit out that way when they get close. That doesn't happen. They don't repel each other, and they don't attract each other either. Lastly, here's what I think is probably the most important thing to keep in mind when we're talking about the kinetic theory of gas. And that's that the average kinetic energy of gas particles depends on the temperature of the gas. The hotter it is, the faster they move. So remember, hotter for gas movement equals faster. This is tremendously important. The hotter it is, the faster these gas particles move. So this kinetic theory of gases, we've looked at a few of the rules that we always want to keep in mind whenever we're dealing with gases. And again, we're going to assume that all the gases we're dealing with follow these 5 rules that we just talked about.
And essentially everything that he just said is listed here. Some of you I know wrote a few things down. Again, the straight line motion is very important. When you're talking about the volume of gas, you're really talking about the volume of a container. Talked about the fact that average kinetic energy is directly related to the absolute temperature. You'll see we're going to be using Kelvin as a unit of temperature here. He talked quite a bit about the elastic collisions and no attractive or repulsive forces between gas molecules. I'm going to skip this right now. We'll come back to it later on. Properties of gases are listed here. One thing I don't believe he did say is that gases have a very low density compared to liquids or solids. That's because the volume is so large that the density then in turn becomes smaller than what you would see, for example, for liquids or solids. So that's one thing he didn't mention. Also, gases are highly compressible. This is very important in the old age homes for example, where a lot of people are using oxygen tanks and they want to be able to move around. So that also very important. The variables we are going to be looking at in this chapter are listed here. I want to point out a few key things. In regard to gases, variables we're going to be considering include volume, abbreviated capital V for volume, and the units for volume will be liters or mils. Please note that 1 liter is equal to 1,000 milliliters. It is expected that you know that. It won't be provided. Most volume when you're talking about gases is essentially empty space, and again, that's one of the reasons they can be compressed. Other variables we want to consider in this chapter are temperature, abbreviated capital T. Our unit here will be Kelvin. Be very careful there. You can easily convert degrees Celsius to Kelvin if you are given 20 degrees Celsius. You add 273.15 to it, and you get 293.15 capital K for Kelvin. And you'll need to know that simple conversion. Another variable we're going to consider is pressure. Pressure, abbreviated capital P, a lot of different units for pressure. Atmospheres, pascals, kilopascals, torr, millimeters of mercury, a lot of different units of pressure. And if you do need to convert between those units, the equivalencies will be provided to you. Now, pressure is force per unit area. The greater the force, the greater the pressure. Force is equal to mass times acceleration. So if you have a child who, let's say, is 20 kilograms, that'll exert some pressure. But if you have a man, and let's say that man is 200 kilograms, when he steps on your foot, the pressure is going to be far more severe. On the flip side, area is inversely related to pressure. So as you increase the area, the pressure decreases. And that's why way up north or in Alaska, when they want to walk around in the snow, they use snowshoes. And snowshoes look like big tennis rackets. They have significant area. As you increase the area, you decrease the pressure exerted on the snow and you won't sink. Well, let's say next year you're going to take your let's say you want to take your girlfriend to the prom and you pick her up at her house and she has these spiky heels on. Well, the area of that spiky heel is very small. And so if she doesn't know how to dance and she steps on your foot, the pressure that she exerts on your foot is really going to hurt. So you better find out what kind of shoes she's getting, and if she's wearing these spiky jobs, you better make sure she can dance. Pressure and area have an inverse relationship. Pressure and force have a direct relationship. The other variable we want to consider is moles. And moles has a funny abbreviation. It's N, not M. A little m is mass or molality, different from moles. Unit MOL. The last thing I do want to mention is how we measure pressure. If we want to measure atmospheric pressure, we use an instrument called a barometer. And the old-fashioned barometers look like this. You had a tub full of mercury with an upside-down glass tube. The atmosphere would exert pressure on the mercury, and you would measure the height that the mercury rises up the tube. Nowadays we have digital thermometers, and I don't think they work based on mercury. Mercury has been shown to be a carcinogen, so we probably don't use mercury all that much. If you wanted to know atmospheric pressure, oopsie, I lost the W. If you wanted to know atmospheric pressure today, we could look in our area. Aberdeen's right near here. And we could get atmospheric pressure. Barometric or atmospheric pressure is 30.27 inches or 1,024.8 millibars, and we can convert that into whatever unit we want. When we do both of our labs, we will need atmospheric pressure, and we can get it this way, or they have a fancy schmancy barometer down the hallway, so sometimes we'll just see what that barometer says. Very often, pressure measurements or other types of gas law problems are done at STP. STP is standard temperature and pressure. It's 0 degrees Celsius and 1 atmosphere of pressure. And we'll come back to that concept a little later on.
Pardon the interruption.
Yes?
Yes, Sarah Koronic for Early Relief.
Sure.
Thank you.
If you want to measure gas that's confined to a container, you use what's known as a manometer. So if you wanted to check your tire pressure in your car, if you didn't have a digital readout, most of the cars, newer cars now do have a digital readout, you could use a manometer. Some units of pressure are indicated here. You're probably familiar with psi, pounds per square inch. That's what you would have in a bicycle or a car tire. And the equivalencies are listed here, and they would be provided to you, so you wouldn't have an issue. You don't have to memorize them. Let's do two simple conversions to make sure we remember the factor label method. I have every confidence we do. You guys are very good at the math aspects. In the first example, it says 803 millimeters of mercury, which is a unit of pressure, and we want to convert that to atmospheres. How would we go about doing that? Look for the conversion, if one exists, for both millimeters of mercury and atmospheres. We have 1 atmosphere, 760 millimeters of mercury. And all we need to do then is divide. We have 803 divided by 760. And that's 1.06 atmospheres, maintaining 3 Siggy Wiggies. The second problem is equally as easy. You are very skilled in these types of conversions. 3.25 kPa, and you want to know bars. What do we do? So at the last position, 1 bar is 1,025 pascals. We're in kilopascals, so 1 kilopascal is
1,000
very simple factor label method conversions that we went over the first week of school.
So units of pressure, there's a lot of different units of pressure. Be familiar with them and make sure you can do very simple conversions. What we'll explore next time is the inverse relationship between pressure and volume, the direct relationship between volume and Kelvin temperature, and we have a very cool lab on that one, the direct relationship between pressure and temperature, and then we can put all of these variables together into a combined gas law, and that's what we'll get into in our next class. That will require a lot of practice, which you will be provided with so that you can master these simple concepts. Any questions in regard to simple gas properties, the variables we're going to be exploring?